If I tried to solve this one the way that I normally do, I obviously would subtract 1 to both sides, and I would get something that says x squared is equal to -1. Well, that's fine. And normally what we would do is we would try to take a square root on both sides, and we would get something that looks like this. And normally this was not possible. There was no way that I can multiply a number by itself and get to a negative number. That's just not possible because I can't do -1 times -1, and I can't do 1 times 1. That's just not there. So these are called imaginary numbers. And it's when you take the square root of a negative number. So a couple of key facts that we are going to use throughout today is that I is the same thing as the square root of -1. They kind of are interchangeable. It's kind of what it represents. So the good news is I squared, if I tried to square both sides, it's going to equal -1. So these are some really crucial ideas that we're going to see throughout this lesson. So how is this actually going to work? Let's try simplifying before we begin to solve. So on here, what I always like to do is I still leave this root and I break up the number. So -5 is the same thing as -1 times 5. Well, the square root of -1 is I, so I'm going to take that out. And then square root of 5 is not pretty, so I'm going to leave it just as 5. That's it. We done. Well, the good news is I'm going to leave the 2 on the outside, and then I have square root of 25. Well, that's the same thing as -1 times 25. And I know the square root of 25 is 5. So final simplification is 10i. 2 times 5 is 10, and then the I just kind of gets attached. Final answer, that's how we're going to simplify. Because here's the good news. The negative is on the outside, and we can have negative square roots. I can do negative root too. I think we've seen that a couple before this particular topic. So no I's are going to be involved. The 40, though, I'm going to leave this negative on the outside. 40 is not a perfect square like 25 is. But here's the good news. I do know that 40 is the same thing as 4 times 10. Ah, I know the square root of 4. That happens to be 2. Square root of 10, well, that's not going to get any smaller. So I'm just going to leave it as square root of 10. So there are ways that we can continue to simplify roots. All right, on D, I see a negative underneath. So I am going to have some imaginary numbers. So I do the same thing. I take the imaginary part out first. I like doing that. And then I can kind of simplify a little more. Oh, okay, so 8 isn't a perfect square, but I can do 4 times 2, and 4 is a perfect square, so I can take a 2 out. You'll see I yanked the i's out because I have square root of -1. And now all I'm going to do is just multiply those pieces back together. So I've got 2i squared times root 10, 5 times 2. I think that step is particularly sneaky, so I did 5 times 2. That's where I got the 10 from. And then I times I is I squared. And we saw that I squared is the same thing as -1. So I can replace that and just make that -2. If you're wondering where that came from, so I just did this instead. So I squared is the same thing as -1. And that's where I got the -2 from. And that's a final answer. So what I love about this is this one started off with imaginary numbers. But in the end, it worked out to a real number. No imaginary pieces involved. And I think that's where you can start to see how they can help us, because they give us a chance to find solutions and they give us a chance to simplify, and everything can actually work out in the end. On this one, I can see there is a minus sign. So all I'm going to do is distribute that minus sign to both pieces. So this becomes negative, and this becomes positive. So you can simplify complex numbers the way that you do everything else. Think of it along the lines of like terms. The biggest thing is the order. Order will matter with these. So I have 2 minus 14, so there's negative 12, minus 3i plus 7i gives me positive 4i. So these kinds of numbers are called the complex numbers. You have an imaginary part and you have a real part, and they are written in that order. It always goes the real number and then the imaginary number. All right, this one. So on here, same exact concept. I think you probably already are using some intuition where you're just going to multiply a 3i into both pieces. Okay, well, there's 6i, and then I've got 3 times 7, so 21. I times I. Oh, it's another I squared, and I think I'm going to pull our little quick fact up here from the previous page where we have I squared is the same thing as negative 1, so that's always my little tip right here. So I'm going to change that out. So instead of leaving it as I squared, I can keep simplifying. So keep simplifying if you can. And then you'll see I've got 6i and I've got positive 2. And remember, real, then imaginary. So 2 plus 6i. All right, here I see something is squared. And I think these are always also very tricky. But to help you simplify these, always write it twice. Do not distribute the square because the square says it's times itself. So on here, I know some of you like the FOIL method. I like to double distribute. So you'll see I put the 2 into both, and then I put the minus 7i into both. So there's my color-coded pieces. So I have 2 times 2 is 4. 2 times negative 7, there's my negative 14i. There's another negative 14i in the orange. And then, negative 7 times negative 7, so there's positive 49, and then I squared. So you can see that now I can combine my like terms. So I have minus 4, minus 28i, and you can see that I've replaced I squared again with negative 1. And again, just combine those like terms. Now we are going to try to solve. We're going to switch gears. We got good at simplifying. So with solving, I'm going to give myself a little bit of space here. Normally, we would try to complete the square and add stuff to both sides, but I want to show you another way that you can solve these. Because on here, I'm just going to try to subtract 64 on both sides. We're going to see what happens. So you got those are going to cancel out. So I have 16x squared is going to be left there in orange. And then I've got negative 64 stuck on this side. All right, I'm still solving for x, so I'm going to divide by 16 on both sides, keep everything nice and balanced. And so now what we can do is square root both sides. I do see a negative underneath. I do have imaginary. So here's the good news. I'm going to take the I out because that's the imaginary part. Square root of 64. Well, that's the same thing as 8. And then I see square root of 16. Well, that happens to be 4. Well, look at that. 8 over 4. Here's the biggest thing. Remember when you take square roots? Plus or minus. So we have plus or minus 2i. No real part on this one. Final answer. On here, so really we've encountered a couple different situations so far. We've encountered one where we have 2 real solutions. So that one, when we sketch it, it kind of looked something like this. So it crossed the x-axis and it crossed 2 times. 2 real solutions. They weren't always pretty, but they were 2 real solutions. The other one that we've run into is where we've only found 1 real solution. So that particular example is where it touched the x-axis but only in one spot. So we only had one possible root. And the last one that we saw usually did something like this, where it never crossed the x-axis at all. It's almost like we couldn't see where it crossed the x-axis. So that means two imaginary solutions. So we used to say that they were non-real, and I think now you know why. Because we literally could not see the solutions because they're imaginary. So now we're going to try to solve for all solutions, both the real solutions and the imaginary. Ooh, if I try to factor, and I know some of you preferred this X method, which I really appreciate seeing. So some of you preferred to say, okay, it multiplies to 12, and then it adds to -6. And I can sit here and I can think, well, unfortunately, there's nothing that would work. It's not going to factor, so I'm going to try completing the square instead. So that says I need to move the 12 over. So now it's negative. No GCFs, which I love. So now I'm going to jump and add a blank to both sides. All right, and now I just got to figure out what works. I'm going to put complete the square. So if it doesn't factor, I can always do that. Right, complete the square says I take whatever's in the middle. So this one happens to be -6. And perfect square goes up there. So I've got +9 and +9 to both sides. And now you're going to do your favorite thing, your favorite factoring, perfect square trinomial. So it goes super fast. Aha! -12 plus 9 is -3. Now I kind of do what I did before, where I'm going to root both sides. Ooh, square root of -3 means I'm going to have an I in there. So I'm just going to take the I out. And then just be sure at the very end to add 3 to both sides for your final two solutions. Be careful, order matters, because you can see the imaginary part is the second piece. So order matters for these. Well, I can't divide by 2 first because 5 divided by 2 is not pretty. So unfortunately, I'm going to just have to move the 5 over. And that's okay. I do have a GCF. There is a 2 hanging on, so I do need to factor that out. And then add something to both sides. I think this one is always tricky because you need to do 2 times 1 to make sure it goes on the other side. Perfect square, it factors beautifully. It looks like I still get to equal -3 this time. Now I divide by 2. Now I can clear the 2 out. And then I just need to make sure I square root both sides. And I see the imaginary part right there. It's underneath. So just be sure you take out the I, which sounds really kind of graphic, and then subtract the 1. And again, the real part, and then the imaginary. So you have 2 roots, 2 complex roots. So now we can actually keep going. That's why I like complete the square. It gives you all of the types of roots that you can possibly have. All right, this next one's a little interesting because it's having you determine whether this is a solution. So normally what we would do is I could complete the square and try to solve, but I already have a possible answer. So all I have to do is just substitute the x in and see, do I get a true statement or not? Do I equal 1 or is it something else? So I'm going to square this piece. So I'm going to have to do 3 squared and I squared. So there's 9I squared. And then here I did 4 times 3. And I'm going to simplify a little further because I think you can see here's I squared. So it's the same thing as 9 times -1. And then I'm going to keep simplifying. Okay, I'm pretty sure we can pause right here because this side is a complex number. Well, this is telling me that a complex number is the same thing as a real number. Those are not the same. So on this particular one, it is not a solution. Not a solution. It's something else. Doesn't matter what it is because that was not the question. It just says, is it a solution? All right, I'm going to plug this in. I think now you're going to start to see where simplifying is going to help us because I do see a square. So please be careful and write that out twice. So here I multiplied by -6 to both pieces. And then that purple, you need to expand it. So that's where you can do FOIL. You can do double distribution. So here you kind of see where I got all of that from. And then I'm just going to try to combine a couple things together that I can, like all of the i's. So here's 6i that I combined. You can see that I changed the I squared to -1. So there's kind of where I'm making all of those kind of steps happen. And what I love about this is I'm just going to start canceling some things out because I can see really quick positive 6i minus 6i. I can see 9 plus 10, so there's 19. Oh, minus 19 is 0, so yes, it is a solution. So this one actually worked out really nicely, but you have to know to simplify. I love ones like this where it's asking, could I give an example where I want to subtract something from here and I would get a real number and I need to show that my answer actually works. So on something like this, basically, if I need this to be a real number, I just need to make sure the 3i actually cancels out. So one possible way is I'm just going to make 1 3i. And I picked 5. I like 5. I think it's kind of nice because when I subtract that, oh, I can see that the i's canceled out, and that's a real number. 3 is a real number. A couple other ones that you can do. So if you thought of this one as an example, so 3i, and it just says, what can I subtract from that to make it a real number? Well, I could subtract 3i because, again, those would cancel out and I would be left with 8. So that's another example. There's a bunch of different examples. The biggest thing is you just want to make sure those i's cancel out. It says that Sheldon is arguing. What a shock. Leonard is claiming that I can multiply, or the product of any imaginary numbers would give me a real number. So once I multiply two numbers, it says I should work. And is Leonard correct? We can possibly explain why. So I'm going to show you two different examples. One of them has them being multiplied, 3i times 4i. And the other one, I've changed it because I've added some pluses in between. So here, I just did straight multiplication. So 4 times 3, I times I. And, oh, it worked. -12. That is a real number. I can put that on the number line. But here's the problem. Let's say I put these pluses in the middle and I tried to multiply them out. So here you can see I did 3 times 4, 3 times I did 4 times I times I. Well, that is still a complex number. So unfortunately, Leonard is incorrect. Leonard is incorrect. So it doesn't always work. And I like showing you a little bit of both. Thanks for watching. We're going to do a little bit more practice in class.